Hello everyone, my name is Vishnu Pendyala. My student Sowmya and I will be presenting on enhancing the experience of passengers of a rapid transit system using machine learning and Neo4j Graph Database. Um, we all want a sustainable future, and transportation is often the largest contributor to an individual's carbon footprint. Actually, transport alone accounts for around 25% of global carbon dioxide emissions. It is high time that we all use public transport for commuting, particularly for long distances. One of the deterrents to using public transport, at least for me, is the uncertainty in predicting ridership. We want to know how crowded the train is before getting on. To the best of our knowledge, neither Google Maps nor the transportation providers do this prediction for us. So in this presentation, my student Sowmya Kuruba will present on using machine learning and Neo4j Graph Database on the data collected from our local rapid transit, BART, to do three things. One is predict ridership. The second is compute commute time reduction if BART wants to come up with a direct line instead of connections. And the third is to answer user queries relating to various aspects of the commute. Machine learning and graphs make a powerful tool set. We all know that. That's probably one of the reasons we are here in the session. Graph databases are best for complex query processing, and machine learning is great at handling uncertainty, making predictions, and assessing scenarios. So this academic project, by the way, we have no connection with BART, the rapid transit system. This is just an academic project, and hopefully if BART is interested, we can sell our ideas to them. But for now, it's an academic project, and it combines both machine learning and graph databases to provide value to the commuters. There are many applications using machine learning on graph databases, but this one does the reverse. It uses graph databases on the results from machine learning. So for more details, let us hear from Sowmya. Over to you, Sowmya. Take it away.
Thank you, Professor. Now that we have an idea about the project objectives, let's look at our project flow. So our project's primary data set is sourced from the official BART website, which is accessible at bart.gov. It has a comprehensive set of data which has the information regarding ridership fare, which is crucial for our analysis. We are going to consider three types of data, mainly the fare related data, which is sourced from bar.gov. Originally, this data was in the form of normalized table, and we had to clean it and merge the table so that it is compatible for the Neo4j graph creation. We also have bar time related data, which is obtained from Google Maps API. So basically, this represents the travel time between the source and destination station. Our primary ridership data, which is used for ridership prediction, is sourced from BART.gov for the year 2023. This data goes under certain cleaning and processing so that it is compatible for our machine learning development, model development. So this is the project flow. As we looked at the data collection and data preparation, after which we are going to construct the graph. We have constructed the graph in the Jupyter notebook using Python Neo for the database connectivity with our local Neo4j. We are going to run some Cypher queries to create the graph and update the graph within the Python. Once this Neo4j graph is created, we move forward with our model development with the ridership data. Specifically, we are going to use the XGBoost model. The output of this model would be the ridership prediction between the stations. So we want to convey this insight or analysis somehow to the commuters. So for that, we have come up with the intuitive web application. The backend of this application is done using Flask. and we have the database connectivity using Neo4j and Python Neo, again within the Python. And the front end is a simple HTML and Bootstrap. The result of this web app would be a ridership estimation for a given hour, week, and month. We also additionally provide the time and fare related data for the given source and destination. So this is the overall flow of our project. So before jumping into the creation of graph within the Neo4j, we wanted to model the graph to understand the graph structure. So as we can see, the stations are the nodes with the property station ID and station name. The relationship between the nodes are fare, travel time, and ridership. The fare relationship has the property of ridership category associated with its fare. And the travel time relationship has the property time, which signifies the travel time between the source and destination station. Ridership has the property ridership count that tells how many travelers are traveling between the uh, two nodes. So basically, this relationship is created from the output of the ML model. Here, the fare and ridership relationships are one to many, meaning there's a relationship of fare and ridership existing from one station to every other station. However, the travel time relationship is modeled in a different way. The travel time relationship exists only between the connecting station. So, if at all we have to consider just the station and travel time, the map or the graph would look exactly like the BART map. So, this will allow us to use some traversal techniques, and this would be a foundation for our different analysis. So there's two snapshot in the slide. You can see that there's a BART map and also the Neo4j graph that we have created. We can see that the Neo4j graph directly resembles the BART map. For instance, if you consider the station 11, which is McCartan, it's a junction in the BART map. The same thing is represented in our Neo4j graph. This was possible because of modeling the travel time only between the connecting stations. After the graph was created, we went ahead with the machine learning model development for the ridership prediction. So let's look at some of the parameters that we have considered for the construction of this model. So we're going to use XGBoost regression model. The input features for this model would be the source ID, destination ID, hour, day, week, and month. So the output or the target feature would be the ridership count for the specified period. The learning rate is 0.01, and we have run this model for 60 times. As you can see from the right hand side graph, you can see that the root mean square error is decreasing as the model is learning. Now that we know all the technical details of this project, let's dive into the code and look at the demo. So as we mentioned, we have used Jupyter Notebook to construct the graph. You can see that we have used a Python Neo driver to connect to the Neo4j and create the graph. We have imported our data set fare and time. This is the fare data. This is the time data. We have established a connection with the Neo4j local server by giving the server address and auth. So this is a function that's used to create the graph. We're going to create the graph with the stations and the fare relationship initially. So the fare relationship will have different categories as its properties, after which we're going to update the graph with the travel time relationship. So we're going to call this function, and as you can see, I've already called this, and the station nodes and the fare relationship has been successfully created, and the time relationship has been updated to the created graph. Let's look at how this looks in the Neo4j desktop. So we can see here the graph is constructed. There are 50 stations, just as in the BART map. And we have two types of relationships, that is fare and travel time. The fare relationship, as we mentioned, exists from one station to every other station. And the travel time relationship exists only between the connecting stations. The number says it all. So after the creation of graph, we went ahead with the machine learning model training, and we have saved the model, and we're going to integrate it with our backend. As we can see, this is our machine learning model, and this is the backend. The backend is created using the Flask. So we're going to use Neo4j package to connect to the Neo4j local database, and Python Neo is used to work within the graph. We have also imported the XGBoost package to work with the model that we have created. We have established the connection with the local Neo4j. So we have different functions or methods within the backend code with the Cypher queries. So this is the real-time queries. We're going to query in real time with the Neo4j backend to get informations such as for instance, this is a Cypher query that gives us the total time between the source and destination. So when the user selects the time related info, we're going to give the output in real time. So this is a Cypher query that gives the fare with respect to the ridership category. As we can see here, we have integrated the model within the backend. This ridership prediction will be made between every pair of stations in real time, and this predictions will be updated as the relationship between the stations into the Neo4j server. Once this updation for all the stations are done, the users can go ahead and select the source and destination station and get the total ridership predictions. As you can see, this is the Cypher query that predicts the total ridership by summating the ridership count within the path. So enough with the code, let's look at the demo. So we're going to run this backend file. Yeah, so our web application is hosted in this link. Yeah, so this is our intuitive UI or web app. Let's go ahead and see how the BART ridership prediction works. Yeah, as we mentioned, the input parameters is the required time period. So we're going to select a time, the day, the week, and the month. And when we click on the calculate ridership, so the ridership prediction is made on all pairs of station. We can see in the backend that the model is run for all pairs of station and the predictions is made. And in real time, these predictions is getting updated into the Neo4j database. We can see that here in the Neo4j desktop. If you observe, there are new edges that is created with the color yellow that represents the relationship nodes. Just like the fare relationship, the ridership relationship also exists from one node to every other node, which means that there's a ridership count info that exists from one station to every other station. And to get the total ridership, we are going to use the path from source to destination. We are going to summate the ridership count within this path for from which we can get the total ridership between the source and destination. So the estimation will be made on all pairs of station. So the prediction is completed, as we can see here. Now let's go ahead and select the source station and destination station. And clicking on predict, we can see the estimated ridership prediction. The estimated ridership prediction from source to destination 4. The first one suggests that there were exactly 4 travelers who boarded the train at the source station and got down at the destination station. The estimated total ridership count from source to destination 7 suggests that there were total 7 travelers between the source and destination station. In addition to this, we are also providing the information about the travel time and fare. So when we select the source and destination station and click on the travel time, we can see that the estimated time to travel from the San Bruno to Fremont is 74 minutes. And these are the price with respect to the ridership categories. So this comprehensive approach enhances the commuting experience for users and makes the traveling plan for BART more convenient. I hope you enjoyed this demo. Now let's quickly look at the key takeaways from this project. As we saw that Neo4j worked really well for our transit system. So Neo4j excels in handling complex relationships, making it ideal for modeling and managing the intricate connections within the transit system. The Neo4j seamless integration with the Python through the libraries like Py2Neo which is used for data connectivity to the Neo4j backend, highlights its compatibility with popular programming languages. It also facilitates easy data import, management, and real time interactions. The project showcases how Neo4j relationships can be updated with the results of the machine learning model like XGBoost, expanding its utility in advanced graph analytics and predictive modeling. By integrating the Neo4j with user-friendly Flask application, the project underscores how databases can be utilized to deliver the real-time insights to the end users. Thank you. I'd like to extend credits to my friend Madhura Batsuri for helping me with the web application templates. If you wish to connect with us, you can reach us out on LinkedIn or Twitter. Thank you. We are open for questions.